All right, so you can see my screen and everything as usual, right?
Yeah.
Yeah, excellent. So today's paper that we're having a look at is a bit of a different one. So it's one of these practical papers that you do. So you've had a look at it. I don't know exactly how much of it or what you'll have done with one of these. They're quite different. So what did you think of it? First of all, would be my first question.
So what I find is designing the experiment without any tools and stuff, just doing it straight off and designing the experiment on paper. I've never done that, and I was quite confused by question 1, but question 2, I felt was actually quite okay because they give you all the data that you need, and it's just solving for the answers.
Question 2 is reasonably. It's essentially a fairly standard question, except it's all about experimental techniques. But fundamentally, it's the same idea as a regular paper, isn't it? You know, lots of calculations, lots of graph drawing, more calculations.
Exactly.
Yeah. So it's about sort of percentage uncertainty in graphs instead of, say electromagnetism. But it's normal kind of stuff. So it's probably useful to have a look at question 1 for most of our time here, and kind of talk about where we're heading with this. So am I right in thinking that this is the first kind of week length of thing that you've done on A2 physics?
Yes, it is.
Yeah. So obviously the aim isn't for you to know everything by the end of this week, but yeah, so this is the first time you've seen this. So for now, it's worth probably just sort of having a talk about what they're after. And one of the useful things for that is their actual mark scheme. So that's all just lots of writing. How much have they given you? Yeah, so they're not expecting a great amount of writing from you, really. They haven't given you a huge amount of space over there. So yeah, let's keep the text by there. So one of the things that's worth having a look at in their mark scheme. Do you have their mark scheme with you at the moment, or?
I can get it up quickly.
I would grab it up because it's quite illuminating in this particular case, and I think it makes for quite a useful kind of schematic for what your answer should look like in structural terms.
Okay. Let's see. No, that works. There. Okay, yeah.
All right, so the mark scheme for question 1 is rather interestingly divided up, and they've split it up into 4 sections. So we have defining the problem, methods of data collection, methods of analysis, and additional detail. So fundamentally, it's actually those first 3 points are essentially the structure that they are looking for you to have in your answer. And things like that are quite useful because, and this is very much exam technique rather than useful things to know, I would say. But if there is a specific structure in the mark scheme, you want to match that as much as you can, just because it makes it easy for the examiner to spot where you should have got the marks. And, examiners are a lot happier if you're making their life easy than if you're making it a pain to find whether you've got the marks or not. So they're defining the problem point is one it's the sort of thing that they're always very fond of in these things. And it's this kind of generic idea of, what is what was the term they always used at GCSE? How science works. That was what they liked. So state what the independent variable is, what the dependent variable is. Ideally, state. I don't know. Maybe it's on the other one, but ideally state things that you need to keep constant as well. So control variables, things like that.
Okay.
So they've given us 5 points here. So procedure to be followed, measurements to be taken, control variables, analysis, safety precautions. Right, so that's an interesting mismatch. So their 5 points don't match up particularly well with the points in the mark scheme, but they'll do. So, what are they fundamentally asking for? We've got magnet falling down copper pipe, V as it leaves the pipe, suggested that we have this relationship, design an experiment to test the relationship between V and B. All right, so yeah. So they're deliberately giving you as little as possible to start with here, because they want to give you as much. You're clearly very popular today.
My dad's texting me over and over again.
So they're trying to give you as little as possible to allow you to come up with something different.
Yeah.
Oh wow, that's okay. So there are some things on here that I would admit it would never have occurred to me to do. But fair enough. So where should we start here? That's the question, really. So defining the problem. In that section, they're talking about essentially the kind of ideas behind it. So, what's the dependent variable? What's the independent variable? I.e., what are you going to be plotting against what? So in this case, we're varying B, which is essentially the strength of the magnet we're dropping, and we are measuring V, which is the speed that it's coming out the bottom here. Yeah?
Yep.
I think one of the most useful things then is to essentially just move into talking about, okay, what am I really going to do? That's our kind of methods section, and that's what are we really going to do? So those are our two variables that we're actually varying and measuring. So what are we going to need to keep the same? What are we going to need to control to make this experiment actually reasonable? That's the next and one of the biggest questions to ask yourself. Because that is what actually determines your methodology. So have a think and suggest to me some things that we're going to need to keep the same in here.
The angle of the tube.
Yep.
The length of the tube.
Yep.
The distance that the piping is from the tube, the magnet. The inside, so like the diameter of it.
Okay, yep.
I think that would be...
All right. There's one other that I would suggest is pretty important, but... It's almost not mentioned in here, actually, which is a little odd. Oh, yeah, it is. Okay. Hang on. So we've got 1, 2, 5, 6, 7, and 6. Okay. Oh. All right. Yeah. So, the other thing that I would say is most important is to recognize that if we're varying B of an actual physical magnet, then we're going to have to actually change out the magnet.
Right.
Therefore, we're going to need the mass and the shape of the magnet to be the same.
Right.
To ensure that the actual change in the physical magnet isn't the main factor in how far in what's changing its speed. That's one of the ones in the extra details, which is why I was confused for a minute. I would argue that that's not really an extra detail at all. That's a pretty important thing, but there we go. Yeah, so control variables are a useful one to think your way through, because they're going to determine most of your actual methodology. And then it's about thinking of, okay, ways to make sure that they're the same. So we can keep the length of our copper pipe the same by trivially just using the same copper pipe, right? That one's fairly easy. You said keep the angle of the pipe the same. How are we going to do that?
The suspension of it, just clamping it to a spot, I guess.
Yeah, so I see that's the thing. I would. Oh yeah, okay, yeah. So yeah, that's a good idea. Yes, so suspend it or clamp it to a spot or something like that. Realistically, I would say probably one of the best ways to solve both of those problems in one go would be to clamp it to a table and make a hole in the table for it to fall through. But using up a table for this experiment might be perhaps a little expensive. But regardless, they aren't really interested in practicalities. So if you tell them to drill a hole in the table, as long as it's a theoretical experiment, they aren't really too worried. So that's the other point that is worth mentioning, is if you can think of an easy way, even if it sounds ridiculous, do it.
Okay.
So, and if there's some bizarre over-technical equipment that you would like to use, just do it. Because they're never going to complain at you demanding to be allowed a particle accelerator or something like that if you really want one. Not very useful in this particular case, but they can't complain because they don't say anything about it has to be cheap equipment or anything like that. So there's some interesting examples of that in the Mark scheme of sort of light gates and computer-based motion detectors and stuff that they're using to see when the magnet's falling out, which is entertaining. All right, so we have. Okay, there we go. So we've talked about the measurements that we need to take and the control variables. So our procedure then. So we've said we're going to, clamp our pipe to keep that the same, and we're going to need to use magnets of the same mass. So the last thing we going to work out is, okay, we're varying B by just dropping magnets with different values of B down. How are we going to measure our velocity of our magnet as it falls out the end?
So from the release, I guess, let's use light gates then and put one at the bottom. And since it has to fall from rest, you can use like a mechanical arm to release it. So it starts the timing exactly when the mechanical arm releases it.
Okay. That's interesting. Okay, they don't actually say anything about that. Okay. And so that's another good point. Is it's surprisingly hard to actually release things from rest. So it's good that you thought about a way of doing that, but it wasn't on the mark scheme, sadly, in this case. However, so there is an important point here, right? Which is, as our magnet falls down this copper pipe, is its speed going to be constant?
Probably not.
It can't be, right? Because it's starting from rest and it's falling, so it's going to have to accelerate it some way.
Yeah.
So is measuring time at the top and time at the bottom going to be a good way to measure its speed as it comes out the
bottom? No, and I guess you could take the average off that.
So what you're going to need to find is, essentially time at 2 points here.
Yeah.
Right. So sort of, something like see when it comes out initially, and then when it reaches some fixed distance below that. That's going to be how you're measuring your speed.
Okay.
So they suggest, I think one of the nicest suggestions that they've got is motion sensors attached to a timer or something, right?
Yeah.
So that and they'll, presumably your timer would sort of stop or record when it passes, and so what you'll get is a T1 and a T2, and then you've got a distance d in between here, and so your velocity is then just going to be d over T2 minus T1. That's so you can. What is useful to realize about these questions is that as long as you don't go too ridiculous, they aren't completely set on you knowing the specifics of real world equipment as such. So if you can imagine something fairly reasonable that would be useful, go for it. Right. So here we're saying, I want a motion sensor. Right, you don't need to be any more specific than that. You don't need to know anything about motion sensors. You just want to say, I want something that'll notice when our magnet falls past it.
Yeah.
So it's going to be, and I would suspect that this is a theme here. So, and this is partly me kind of preparing you for almost the next time that you come through here and do this, which is, so, focus on this kind of idea of a very generic things. So, motion sensor, or, mass measurer, or, just something generic that will detect things rather than trying to go for specifics. Because what they're really after here is for you planning out an experiment logically and measuring the right things in the right ways, rather than you knowing specific pieces of equipment. Does that make sense?
Yeah.
So the reason that they haven't, because you said you found it difficult because they hadn't specified any equipment or stuff, there is a reason that they haven't done that. And fundamentally, that's because actually they aren't that worried about what equipment you're using. They're worried about the measurements that you're taking. So as long as you imagine some way of measuring it, they are going to be happy. They're very, in the mark scheme, they say, method to determine time at bottom of tube. That's their so some method to determine a time interval coming out the bottom of the tube. That's all they want. As long as you've come up with some way of doing that, they're happy.
Okay.
If you determine that you would like two, I don't know. I was going to say two hamsters, but I don't think that'd be very useful. But if you determined that you wanted two intelligent hamsters sitting there with notebooks and measuring the time, then they'd probably be okay with that. If you
I don't think I'd risk it.
I wouldn't either, but it's worth me making this point because you said you were worried about the equipment and stuff.
Yeah.
Don't be.
Okay.
So yeah, this is your procedure point, right? This is your procedure by here. So some way of measuring the time difference at the bottom of the tube. The other point is that you're going to need a method to measure your B, your magnetic field. That one is a little more specific. So what I would suggest is, given that you have these experimental papers, what I would suggest is that you make maybe a sort of notebook or something. That's an A, not a O, isn't it? That's supposed to be an O. Make a notebook of some description where you kind of, or find a list online or something, I don't know, but get yourself a list of essentially what do I use to measure what, if that makes sense.
Yeah.
So, if I'm measuring velocity, motion detectors over a time interval or something like that. If you want to measure magnetic field, in their mark scheme, they have said you could use a Hall probe. So I would just take a note to yourself of saying they are happy for me to just say use a Hall probe. You don't really need to worry about what a Hall probe is. You just need to write it down.
Okay.
So yeah, they want some specific piece, so you can't just say measure the magnetic field. They want to know how you're doing that. You could come up with some weird convoluted way of doing it. I would just know the name of some probe that does it.
Okay.
So, if you want to measure temperature, you just write down, use a digital thermometer, right? If you want to measure electric field, I don't know off the top of my head, but there's probably a name for some kind of electric field probe, right?
Yeah.
It's that kind of idea. Realistically, you'd probably use a voltmeter or something, but that's beside the point. Okay, so that's the kind of core of designing our experiment. So we've and actually that's all we've got to do, right? We've determined how we're going to control the environment. We've said how we're going to measure our velocity coming out. We've said how we're going to measure our magnetic strength that we're putting in. So now all we would need to do in theory is actually do it and just get a whole bunch of different magnets and drop them down and record the velocities. So the experiment isn't too hard to plan out, as long as you kind of separate it into those points. So what things do I mean to measure? What are my control variables? And then finally, how am I going to measure what I need to measure? I think that's a good process to follow in terms of designing the actual setup. Okay? Now, the next part is our method of analysis. And this is a different topic entirely. So this is all about what do we do with an equation that looks like this. So, do you know?
No.
Cool. So this is probably there is more to this question than just these two parts, but we've got half an hour left. So I'm going to spend, I expect, the rest of this lesson talking about this now. Because it's really important to talk about. So let me grab the blank space here. We have V equals V0 e to the, what does it look like again? E to the minus lambda b. That's what they've determined. V0 e to the minus lambda b. This is our relationship. And essentially what they are saying here is that we have some generic exponential relationship. Okay?
Okay.
So, and what we're talking about here is V0 and lambda are just some numbers, right? They're constants of proportionality. We say, if we say A is proportional to B, that's equivalent to saying A equals KB. Yep, you've come across that before. When we say V is related exponentially to B, this is the equivalent of saying that. Okay?
Mm-hmm. Yep.
And what this means is that if we were to plot a graph of, V against B, other way around, B and V, what it would look like is this. And it would go through V0 here, and the lambda would just determine how steep it was.
Mm-hmm.
Okay? Because this is, and this is, just a sort of scaled version of e to the minus x. Are you happy with what that graph looks like?
Okay, yeah.
Yeah. All right. So that's ooh, okay, that didn't do what I was expecting it to do. Yeah. So if we were to try and plot this graph, we don't get a great deal of very useful information out of it. We can spot V0 relatively easily in this particular case because of the way it works, but there is no real way of getting lambda out of this graph.
Mm-hmm.
So there is a specific thing that you do with relationships of this type. And what you do is you take logs. Okay?
Yeah.
So what we do is take logs of both sides. How happy are you with log rules?
I'm pretty happy.
Cool. So we do ln of v equals ln of v0 minus lambda v. All right?
Yeah.
Happy with how we got to that.
Mm-hmm. Yeah.
And now, what I'm actually going to do is I'm going to write that in the other order so that it makes more sense when I do this. And then we're going to move on to a second important point. So, this is important because of the way that you do analysis at A level. So, you are familiar with this equation, right? Y equals mx plus c. What is this the equation of?
It's the equation of graph, or what's called a straight line, I believe.
Yeah, a straight line.
Yeah.
So, what are m and c?
M is the gradient and C is the level off on the y-axis.
Yeah, so C, the term for c is the y-intercept.
Yeah.
Okay. And yeah, so this says, if we have a straight line like this, that is going to be c, and the gradient is going to give us m. This is really useful because what it means is if we are able to plot a straight line graph, we can get information from the gradient and the y-intercept.
Mm-hmm.
And so always your aim in an experiment is to try and turn it into a form where you can plot a straight line graph. That's essentially how almost all scientific experiments end up working. You try and plot some kind of a straight line graph. And what you do is you essentially, and the most useful way to figure it out is to do exactly what I've done here, to write them one on top of the other and line things up. Okay?
Mm-hmm.
And so what you can say is, you can do this sort of thing. So y and x are going to need to be your variables, and then m and c are going to come out of your information. And so what you will end up doing here is you will end up plotting a graph of log of y against b.
Mm-hmm.
Okay? And that will give you a straight line with y-intercept ln of v0, and gradient will be minus lambda. So it would in fact be a, the line would actually look like that because it's negative gradient, but you get what I'm saying.
Yeah.
Okay? this is so important because this comes up in every one of these questions, right? This is the core of A-level experimental theory. This is what this is all about: is getting you comfortable and to understand this idea of plotting different things than what you are measuring.
Mm-hmm.
Okay.
Mm-hmm.
There are other ones. So in some cases, you will plot things like, you will plot y against 1 over x or something like that. Over time, as you see more of these papers, you will come across different versions of what you're plotting against what. Your aim is always to get some kind of analogy with y equals mx plus c that will let
Mm-hmm.
you do this. And so in this case, if you then have a look at the mark scheme, there are 3 marks for saying plot a graph of log v against b, minus the gradient is lambda, and that they've said, so they're just kind of rearranging the 2 equations, and v0, log of v0 is the y-intercept. So those are the points on the mark scheme that they're making. And then there are a couple of, so just writing out this equation by here was another mark. So just rearranging it into this was another mark. The reason for that is that some people will just kind of learn the way exponential things work. So they'll learn that this is the gradient and log of this is the y-intercept. I don't think that's a very good idea, really, so I wouldn't try and just learn it off by heart. So all right, what do we want to say? Has this all kind of made sense so far? I think it has.
I think so too.
How comfortable do you think that you would be if you were given a different, exponential relationship like this one, and going from scratch to do this again?
I think I'd be a bit more comfortable. I mean, I still have to do it a few times to kind of get it into system, but a lot more comfortable than this morning.
Yeah, well, I mean, because this morning you had no idea what you were doing.
Exactly.
Yeah, until you know what to try and do, you don't know that you're meant to be trying to plot a straight line graph. So, yeah, that's not a great deal of use. So let's have a look at this one. So this is a similar idea. So here, instead of log, we're plotting 1 over v against x.
Mm-hmm.
And so this is exactly the same idea. They've told you to do it here, rather than you having to realize it for yourself. But it's the same point that there's a non-linear relationship, but linear relationships are what are easy to plot graphs for. All right, so what I think I might do now, it's a little bit of an odd thing to do, but what I'm going to suggest we do is actually I'm going to talk through the spare points. So you see, I'm going to talk you through the mark scheme essentially, and try and just make sure that everything on the mark scheme makes sense to you as to why it's there. Is that okay?
Yeah.
So what we've gone through so far is, so you've got these kind of necessary marks on the first page of the mark scheme, where you have to have these, and there's 9 of those. And then you need 6 out of 10 of the remaining points. So we've actually covered all the first 9 now. So we're going to go through the remaining ones. So keeping the mass of the magnet constant, we already spoke about that, right? That's one of our control variables.
Yeah.
And then, right, so this is another one, is they are obsessed with measurement. This is another thing to remember, essentially, right? So if you ever talk about some kind of numerical value, it is in your interest to suggest a way of measuring it. So in this case, you remember that we said we're going to have two, what do we call them? Motion detectors that are separated by a distance d. Well, there's a mark available for just telling them how we measured the distance d, aka with a ruler. Right? So when we say I have two motion detectors separated by a specific distance d, if you'd literally add to that measured with a ruler, you get an extra mark.
That's kind of...
It's a bit weird, right? It seems a bit random, but again, what they're trying to get through to you is that in a real world situation, you would actually need to find a way to accurately know the distance you were putting them apart, right?
Yeah.
Now, you wouldn't put them there and measure the distance. What you'd probably do is put one motion sensor at the bottom and then, use a ruler and put the second one 10 centimeters down. But you would need to actually accurately know that distance.
Yeah.
And so it does make sense in a lot of ways, but they're trying to make you be nitty gritty with the details. So yeah, add this kind of idea of always having a measurement system in place.
Okay.
Part 3. Okay, so what we wrote down over here. Again, it's kind of stating the obvious, right? V equals d over t.
Yeah.
V is the distance between our time sensors over the difference in the time. But again, it's something that you would need to do because you're not actually measuring V directly, so you need to calculate it.
Yeah.
So there's lots of marks available for these kind of almost unnecessary points that you would need to do. Okay, part 4 is actually specific to the way you use a Hall probe. But so part 3 is specific to using a Hall probe to measure a bipolar magnet. So, measure the magnetic field at each end and average or something like that. Or, find the Hall field, the field at one specific point on the magnet each time. Basically, what they want you to make sure you aren't doing is if we have a magnet, if we have a series of magnets that look like this, right?
Yeah.
What they want to make sure we aren't doing is that for the first magnet, we measure the magnetic field here. For the second magnet, we measure it here. For the third one, we measure it over here. Because that's going to add an extra level of inconsistency beyond just the fact that they have different magnetic strengths intrinsically. Does that make sense?
Yeah.
So, again, this is actually, realistically, this is almost a control variable, right? The control variable is where on the magnet do you measure? So that's really what they're going for, is measure in the same place each time. So probably the most reasonable one is to say, okay, I'm going to measure right here in the middle of the magnet each time.
Yeah.
So it does make sense what they're doing, but it's kind of specific. Number 5 is a suggestion of calibrating your probe. So a lot of the time when you have probes and sensors, it's a good idea to try and calibrate them against something that you know. So I mean, they haven't made a suggestion here, but so because it's a little tricky for a magnetic field. There's not a lot of super constant magnetic fields, but they might have just said, oh, put your Hall probe in a known field and make sure it's giving the right value. One good thing to suggest, and one thing that will always make you popular with examiners, if you ever do an experiment with temperature, and you are looking to a good suggestion to always make is to calibrate your thermometer using using a water-ice mixture. So like, water with lots of ice in it. Yeah?
Yeah.
That's because water with a bunch of ice in it, so a mixture of the two, is actually one of the most temperature stable things in the world, like in existence. It's actually staggeringly stable at exactly 0 degrees C or 273.15 Kelvin.
Yeah.
So it's actually a very good way of calibrating, thermistors, temperature thermometers, all that sort of thing. They're very useful, actually. So that's just a good one to know about. Water and ice is super, super stable. All right, point 6, safety precaution linked to falling. Oh, yes. So this goes back to up here, on here, they have said any safety precautions to be taken. All right. So analysis of the data, that was, we've covered that. That was all of the stuff with the equation. Any safety precautions to be taken. Now, this is always popular with school syllabi because, everyone in a government is obsessed with making sure that they teach school kids how to not kill themselves when they do experiments. Because, it's generally bad press when students accidentally chop limbs off and things. So, safety precautions. Obviously, a lot of experiments, there aren't really any. Realistically, do you need safety precautions to drop magnets down a tube? Not really. There is, so if you're doing one with temperature, wear gloves, be careful of hot things. I remember I got told off by my teacher when I was doing A-level practicals because we were measuring temperatures, and I put down as my safety precaution, don't touch the hot bits. And they told me I wasn't taking things seriously enough. I was very offended by that, but so yeah, it's often a bit trivial, but it's worth coming up with at least one safety precaution, regardless of how unnecessary it seems. And in this case, they've suggested something about the falling magnet. So have a cushion or something to soften the fall. Yeah, I mean, fair enough. To be fair, there's not a lot else that you can suggest with this as a safety precaution, is there? So, yeah, don't put your feet under the tube. There's another good one.
Or head.
Or head, yes. Yeah. Measure the speed by just sort of looking up under it and getting smacked in the face. That'd be a good idea. Okay, so the last few. So this is number 7 is an interesting one. It's a bit more advanced, which is why it's on the options rather than the necessities. But it's an important one in real scientific experiments. So this is 0 point like it's what do you call it? Zero calibration, something like that. Basically, it's making sure that your measurement of 0 is correct, and doing repeats in some way. So in this case, so one point is you always do repeats, right?
Yeah.
That's always important. So you would actually get this mark for just saying, essentially measure V 3, do the experiment and measure V 3 times for each value of B. Right? You would get this mark. One good suggestion in this case is that, perhaps you measure it 4 times and you do 2 with our north pointing down and 2 with our south pointing down. Yeah? Essentially just to make sure that there's no kind of offset or difference that doesn't get taken into account. Number 8 was for the equation that we already talked about. Number 9 is talking about, so when we plot this graph that we've been talking about, right? Our initial question asked us, it is suggested that this is a relationship. Test the relationship. Yeah? So in practice, we're looking for values of v and lambda. But in theory, what we're actually testing is this equation valid at all?
Mm-hmm.
And so what you can say is, if we plot log of v against b, our relationship is valid, provided we get a straight line.
Yeah.
That's the idea, right? We're expecting a straight line, aka, so, to put it in a more reasonable sense, we're expecting a straight line. So if we don't get a straight line, we know there's something up. And then number 10 was a method of varying our magnetic strength. They have suggested, remagnetize your magnet in a electromagnetic coil or something like that. That's a fancy way of doing it. Honestly, my inclination, and that is a realistic way of doing it. My inclination for you would be to say, just write down, use a whole bunch of different magnets of the same mass with different magnetic strengths. Because it's simpler and easier, and ultimately they're not looking for you to be realistic, they're looking for you to give a decent answer.
Yeah.
So yeah, I would always say go for the simplest thing you can think of in this case. I mean, go for whatever you think of. Don't worry about trying to make it, efficient or, cost effective or whatever. That's not what we're about here.
Mm-hmm.
There's no marks here for, frugality or anything like that. As I said, if you can find an excuse in one of these to demand access to CERN, go for it. All right, so I think as a kind of first run through, that's a good set of things to cover with this paper. We have essentially just stuck to question 1, but that's the most different thing about this paper. Question 2 is essentially like a big question from the other paper, but with different equations in. Right? That's the best way to describe it. Question 1 is very, very different. So I think it's good that we spent a lot of time on it today. All right, so I hope you are happy with that, and I think we'll wrap up there if that's all right.
Yep.
Okay, let me stop
the
stream and